This one is from the Lomonosov Olympiad. Read it once and you will think it's too easy. Then you will try it and you will be stuck. Actually, there is nothing weird in it. You already know everything you need. You just have to think a bit more than you expect. Let's take a look. But before we start, I want to tell you about something I have been working on that addresses one of the biggest challenges Olympiad students face. Every week, students ask me the same questions. How do I start preparing for the chemistry Olympiad? Which topics should I study first? Which resources are worth using? And how do I avoid wasting months on the wrong things? These are not simple questions. I spent years figuring them out through my own competition experience, coaching Olympiad students from more than 30 countries and seeing the mistakes that repeatedly slow students down. On August 23rd, I am running a live workshop where I answer all of these questions in one session. I will talk about the preparation strategies I recommend, the resources to use, the mistakes that waste most students' first months of preparation, and how to build a clear study plan from day one. We will also have a 30-minute Q&A at the end so you can ask your own questions and get direct feedback. I ran this workshop once before in January this year and 60 students from 30 countries joined. The feedback I received most often was that they finally had a clear picture of where to start and what to focus on instead of trying to figure everything out on their own. At the end of the session, you'll leave knowing exactly what to study, what to skip, and how to structure your preparation. If that sounds like what you need, the registration link is in the comments. The link closes on August 18 or earlier if all spots are filled. Now let's get into today's problem. Alright, so here is the problem from Lomonosov Olympiad. And as you can see, it's seemingly easy problem with simple transformation scheme, but it requires a bit more thinking than you initially expect. So we have like a simple scheme here, two pieces of information that A and C are isomers and E and G are homologs. And they want us to find out the structures for all ciphered compounds. Also, they want us to write the equations of all the reactions that are happening here. So we just write those two pieces of information we have. E and G are homologs. E and G are these final compounds in these two branches, and homologs are the compounds that differ from each other by a CH2 group. So basically you can think of it like this: methane, ethane, propane, butane, they're like homologs. They belong to the same class of kenes, but they differ from each other by a CH2 group. Or same as, for example, aldehydes, right? Propanol and butanol, they both have aldehyde group, and one of them has 3 carbon atoms, one of them has 4 carbon atoms. They differ by CH2 group. So that's the meaning of homologs. And then they also tell us that A and C are isomers. So they have given us the molecular formula for C. So if A and C are isomers, so we already know that A should also have the same molecular formula. And this is a bit, I would say, misleading from the author's side, the authors who made this problem, in a sense that just saying isomers might not be enough, because it could be stereoisomer or structural isomer or maybe configurational isomer. Usually when they don't mention anything, we assume that it's a structural isomer. They just share the identical molecular formula, as you can see in this case, but they are different by the arrangements of the atoms. But obviously it could have been just a enantiomers or diastereomer, we don't know. But in the current problem setting, we accept that it's a structural isomer. But for making a problem, it would have been much more precise if they mentioned that they are actually structural isomer, but that's how we will assume. Basically, that's it. And now we focus on the synthesis. We remove that part, and then these two pieces of information, we just wrote it here, that E and G are homologs and A and C are structural isomers. They share the identical molecular formula. This is basically what you have right now. And then this scheme doesn't give us a lot of information, and then we don't have the structure of the final compounds. So everything is ciphered here. So we have to actually start from guessing potential structures for compound A and also for C, because the number of carbon atoms are small. We don't usually do that, obviously, but because this problem, there is no any additional information, we need to start guessing about potential structures. And obviously the first step we can do is basically calculating of HDI, which is 2 in this case, 2 elements of unsaturation. So this can tell us that maybe there is 1 ring, 1 pi band, or 2 pi bands. But I would eliminate the idea of having a ring, because if you have a ring, like 4-membered ring, and then there's a double bond like this, that's extremely unstable. Or maybe you can have a 3-membered ring and maybe something like this. These are all very unstable. Obviously, we can keep those in mind, but they are edge cases. If more obvious candidates do not produce anything meaningful, anything successful, then we can come back to these structures. We are not starting with these edge cases, right? And before even starting that, we can actually start labeling the roles of reagents, right? So obviously in the first case, this is hydrohalogenation. We are using 2 molecules of hydrobromic acid. And also this can help us to actually lock down that this does not contain any ring because it has two elements of unsaturation, and then we have two molecules of hydrobromic acid, right? So it's probably the case that there are two pi bonds that are being saturated, like because the ring will not react with hydrobromic acid. So we can talk more about that later, but the first step is most probably hydrohalogenation. Then we have these alcoholic potassium hydroxide and aqueous potassium hydroxide. Obviously, they have more roles than I just listed here. It could be anything ranging from the hydrolysis of, let's say, amides or esters to elimination and to substitution. But probably in this setting, because since we are not talking about any crazy complex structures like esters, because there's no any oxygen here, or amides, we can just keep this list to the elimination and substitution. And then we have potassium permanganate. That's most probably oxidation, because potassium permanganate is strong oxidizing agent. And about this step and then last step, it could be anything basically. So that's why I'm not putting any definitive role here for the reagents. And we can also think that this B is a bromide, right? Right now we can say that A is probably containing two pi bonds, and then they are being saturated. They react with hydrobromic acid, and then we have a dibromide here. Now, the way we need to approach this problem is actually by focusing on ABC, because A to B and B to C, it's actually isomerization. We start from A, which has 4 carbon atoms, 2 hydrogen deficiency index. We end up with the same molecular formula. So it's actually isomerization. So that's why we need to propose some candidates. So the first one is assuming that A is diene, okay? We are writing here that A is in something like this, okay? Now it's reacting with hydrobromic acid. So obviously, 2 molecules of hydrobromic acid, so we need to do it step by step. So how it reacts with hydrobromic acid. So let's say, because this is like a symmetric structure, and pi bonds are symmetric, so it doesn't really matter which one attacks first. So I'm gonna attack like one of them to hydrobromic acid, and then the bromine leaves, and then I have a positive charge here, okay? And hydrogen is attached, and now this bromine can attack there, but I also have resonance structures here, right? So I need to consider those two cases. The pi bonds can delocalize here, and the positive charge can move to this carbon atom, and bromine can either attack here or maybe here, giving us these two possibilities basically. I will just write it like this. So it's either that we have 1,2 hydrohalogenation, or we can have 1,4 addition. So we have two possibilities here, and we can actually do later. Second, this is the first molecule of hydrobromic acid. Then the second molecule of hydrobromic acid, it can give us either this one, and this is like Markovnikov addition, so this is the only possibility here, or hydrobromic acid giving us, actually here we have two possibilities. Like the original, we can either install bromine here or here. Okay, it's a double bond. This is like sides are equally likely to have hydrogen and bromine. Probably expect one of them be more predominant over other, because if you make a positive charge here after taking hydrogen, you make a positive charge here, you remember bromonium ion. Bromine can have lone pair. It can stabilize that through making a bromonium intermediate. So maybe this positive charge being here is more stable in compared to the case where the positive charge here. But also we can assume that this bromine can have the same effect to here. It can make this four-membered ring. The reason why I mentioned this is because we have seen bromonium ion intermediate. So honestly, even if one of them is predominant in compared to other, that's only slight difference in terms of their distribution. So these are all three possibilities that we can get if we have diene, right? And let me actually label them as B1, and which is my 2,3 dibromo product, right? And then there is also B2, which is my 1,2 bromo compound, right? B2. And then this is my B3, which is 1,3 dibromo product, right? And then we'll talk about other cases for diene, but let's just think about what can happen from B1 or B2, B3 to potential C. Because I need to go back to hydrocarbon. Like I have a diene here, which is hydrocarbon, and then I am having a dibromide, and then I have to go back with this elimination. This is, can be sure that this is elimination because cannot be substitution, right? There is no any oxygen here that like comes and substitute bromine. And also alcoholic potassium hydroxide favors elimination over substitution. I will talk more about that at the end, about the reasons, aqueous potassium hydroxide versus alcoholic potassium hydroxide in terms of their favor to substitution and elimination. But yeah, we can be sure that it's elimination because we are getting back that hydrocarbon again. So let's think about possibilities. Like we can take B1. What's the possibility, right? From A1 to B1? If we can have this elimination, we will actually form A again. We will go back to A again, probably. Because hydrogen and this bromine can be eliminated to form this double bond, and this hydrogen, this bromine can be eliminated to form this double bond. Always that there's other possibility, which is very weird, a lean system. Double bond forms here, and this double bond forms here. That's one possibility. Or can have this where with internal alkene. That's also another possibility that we can think about. So other possibilities, it can go back to the original one, or it can form this weird allene structure. It can form, but honestly, it's less probable because this is not highly substituted, right? Forming a double bond here and also here, they're like, here is fine, but here it's not fine. So probably this is much more possible. So we can actually have C here. So I will talk about this later. So we can keep B1. So A going to B1 and then producing C like this, or a bit less chance we can have this. We can keep this route. The second B2. So what we can have from B2? From actually form, like again, this allene will always be there, but I will not write it because this is like weird structure because we have to oxidize it. You know, it's not commonly seen. We haven't about a lot of allene chemistry. Obviously, we will come back to this again if we see that other routes do not work. But for now, I will not include allene in my candidates. So now B2, what's the possibility? From B2, again, I can have allene, but I can have actually terminal alkene, right? So we can have a triple bind like this, and then this. So like B2 going to this one, which is also another candidate for C that can be oxidized later, right, with potassium permanganate. And from B3, from only route is actually to form allene. Again, I'm not talking about that. Or being eliminated, like hydrogen bromide being eliminated, it can also give A. From doesn't make sense because A and C are supposed to be different compounds, like they're only isomers, not the same stuff. So I am eliminating B3 from the options, okay? So the plausible pathways are A going to B1 and producing internal alkene like this. So in this case, this diene that we see here and this C, this alkyne that we see here, they are isomers. Or going to B2 and producing this terminal alkyne. That's also a possibility. And the reason why I eliminated B3 is because there are two options, allene, or it goes back to the original, which is also less likely because in this case, installing a double bond here, we're installing it here, which is also probably not the case because we want Zaitsev product. We want more substituted product to dominate. So that's, even though I'm saying that B3 goes back to A, that's also not even a major product, okay? So I eliminate it from here and B1, B2, and again, for a summary, B1 and B2 are hydrohalogenation product and they come from 1,2 addition. This is 1,2 addition product, and this is 1,4 addition product, okay? 1,4. And 1, 2, and 4 are hydrogen and bromine being installed across the position. Imagine this is 2, 3, 4. And in the first case, 1, 2 addition, we are having hydrogen here and bromine here. They're just 1, 2. And in this case, we are having hydrogen here and bromine here. Bromine here, they're like 1, 2, 3, 4. Like this is one addition. So B1 and B2 are basically dibromides we have from the diene that we have shown here. So this is the first possibility. And so we will now explore this one. So we have alkyne. So obviously it can be internal alkyne, like this, or alkyne like this, 1, 2, 3, and 4. I would like to eliminate this one from the first time because reacting with hydrogen bromide, it will give us what? This geminal dibromide, 1, 2, like this, right? This also gives the same, right? If it's being hydrogen, adding hydrogen bromide here, we will also form the same compound because of the Markovnikov rule, right? We add, honestly, in this case, it doesn't matter. Let's say we add first bromine here, and the second bromine will also come here, and the hydrogen will go. So we will end up with this, and this is what we call as geminal dibromide. Okay, so I will write here geminal. Geminal dihalide is that those two halogens, like bromines, are attached to the same carbon atom. We call it geminal. When they are in the neighboring carbon atoms, we call them vicinal. For example, in the previous cases, we have like two bromines. They are neighboring carbon atoms. That's what we're calling as vicinal. But in this case, it's a geminal dibromide. And the reason why I want to eliminate is because let's say this is H3 as our candidate, and I would like to eliminate A2. Why? Because you can form this kind of geminal dibromide, and then if you want to eliminate, it will come back and give you the same. Because we want to have form like this first, because it's more substitute Zaitsev product. And the second case, again, we are going to eliminate this hydrogen, and then we will form the same A as before. So that's why I want to eliminate this A2, okay, as an option. I would like to continue with this terminal alkyne, okay? So you have those here, and it's being adding two halogens here, and then we have this, and then it can be eliminated to produce this. That's actually a real possibility, okay? So you have a terminal alkyne, and then it's being isomerized to internal alkyne in these two steps, hydrohalogenation and then elimination. Okay, so this is a possibility. I eliminated this internal alkyne as a starting material so that we can have the isomerization possible. So proposed mechanism can look like as the same as we propose in alkene. We have a triple bond here, and this, maybe this attacks bromide. Okay, bromine leaves,
and we can have this vinylic carbocation, right? Maybe something like this. And then we put a positive charge here, and then bromine attacks, right? And then we form something like this. And then again, the hydrobromic acid can be added again, and then that will give our this geminal bromide. This proposed mechanism that you can see in introductory organic chemistry textbooks, it involves intermediate vinylic carbocation, and it can actually successfully explain the observed regioselectivity, like why bromine is here, because maybe you can suggest that this vinylic carbocation is more stable. But if the positive charge was here, that would be primary vinylic carbocation. But this proposed mechanism is not consistent with all of the experimental observations, because they have done the studies in the gas phase, and those studies indicate vinylic carbocations are actually not particularly stable. Okay, so I would like to mention that here, not particularly stable. And also not just in the context of this reaction, but in general. We usually not propose vinylic carbocation as an intermediate. So studies concluded that this vinylic carbocation, even though they are secondary, they're actually similar in energy to regular primary carbocation. And we know that primary carbocations are not stable at all. And also there are other mechanisms that have been proposed that avoid the formation of vinylic carbocation. One of them is, so we have this alkyne, and I'm gonna write it like unsymmetrical alkyne. One of them has IH, basically a terminal one. And then you have two HX at the same time, right? So HX is here, and another HX is here. This one basically attacks here, and then this attacks here. So your transition state is something like this. R carbon, and then you have a double bond to another carbon, and then the other one is connected to hydrogen here, and then here you are connected to X and hydrogen, right? So this is your transition state. So we call this as a thermomolecular. Also observed regioselectivity, because I would like to have my delta positive charge on this carbon, right? So that this is connected to, and this one is connected to hydrogen, right? Because I want this charge to be here next to R rather than this H group, so that it's better stabilized. So this is the observed regioselectivity. And also this avoids the formation of vinylic carbocation. And also this more complex mechanism is supported in many cases by kinetic studies. And there's a rate expression says K, the rate constant, multiplied by the concentration of alkyne, multiplied by the concentration of HX to the square. So there are two HX that are in the rate determining step. But in the actual case, it's believed that addition of HX to alkynes probably occurs through a variety of mechanistic pathways, all occurring at the same time and competing with each other. So there's actually possible that we can have vinylic carbocation or this thermomolecular process. Having this vinylic carbocation, it probably plays some limited role. It cannot by itself explain all of the observations. Basically, this is what I wanted to talk about, the addition of two molecules of hydrobromic acid to the alkyne. Basically, that's it. So we wrote three possibilities, right? That A as a diene, giving us two products, B1 and B2. And also this A being an alkyne, giving us this kind of isomerization. Now let's evaluate these pathways in the context of the whole scheme of synthetic transformation. So we have this A as a diene, right? And then I will just only write the one pathway with the one product, like the B1. So I have my diene, and then it reacts with hydrobromic acid, and I will only show this B1, which is the 2,3-dibromobutane. And then it gives me this internal alkyne, right, that we talked about it. And then it can be oxidized. We know that alkynes are oxidized to carboxylic acid, and you are just oxidizing it in the middle of the carbon-carbon triple bond. So you actually have two molecules of acetic acid. And then this is just, you have acid, very simple acid, and then potassium hydroxide. So obviously potassium hydroxide aqueous, it can maybe elimination or substitution, but obviously in this case, our substrate is not alkyl halide or anything that has a good leaving group. So we can assume that this is just a simple acid-base reaction. Carboxylic acid becomes carboxylate, potassium carboxylate, like this. So this is E. If we assume this pathway, the diene, then we have to think about then what we can have from this dibromide that can react with potassium hydroxide to give us F, so that in just one step we can get again carboxylate. We need to think about that. So if we assume that this is also substitution, maybe it's the case that A and C and F are all isomers. Maybe problem doesn't tell this us. They only tell us that A and C are isomers. But maybe F is also isomer, and the aqueous peroxide also does this elimination. And then maybe F is, I don't know, what F can be again A. Obviously, it's not possible, right? We can eliminate this double bond here. We can form A again, but it doesn't make sense. Or we already saw the one possibility of an internal alkyne. What's another possibility? Maybe we can think about allene now, which is weird again, but we need to think about it, right? Allene. But allene reacting with iodine, potassium hydroxide, giving us some, we have never seen this reaction. We have never seen the interaction between allene and iodine under basic environment so that it can give us some carboxylate. I would eliminate this possibility, right? So because of the fact that I cannot move forward, I'm actually eliminating this whole idea of diene going to 2,3 dibromobutane. I'm also eliminating this possibility, right? Because yes, maybe this branch makes perfect sense. I can go all the way, but I cannot do anything, right? I can even think about substitution, right? OH substituting 2 bromine, so I get something like this, maybe from 2,3 dibromobutane. I go 2,3 diol, but then how is it gonna give me carboxylic acid, right? Carboxylate with iodine. I also haven't seen this reaction. So maybe iodine is oxidizing agent. Iodine 0 goes to 2 iodine minus, right? So it's 0, it goes down. That means it's oxidizing agent, right? So it oxidized something. Maybe, I don't know, carbon-carbon bond here is actually susceptible. So because we have this malaprate oxidation that takes diols, right? You have a diols, and then you can have sodium periodate, right? You can react that, and then it will cleave this carbon-carbon bond. There is this reaction, right, that also acetate 4. That's also another possibility that takes diol as an basically input. Our substrate is diol, and it cleaves, it oxidizes carbon-carbon bond. Maybe this is possible, but I don't think iodine is that strong in this case to induce. But even if in that case possible, we actually end up with this COOH in the best case scenario, actually, which is the same as E. They are not homologs. So even in this very edge case that's possible, we do not get homolog. We are only getting the same compound as E, which also doesn't make sense. So we eliminate this possibility. So we explored this case. Now I would like to talk about another case where I take the diene as an initial substrate and then hydrohalogenate, but this time it gives me 1,2-dibromo compound, right? Bromine here and bromine here, right? And then from C, and then I can have, again, alene. I'm not including that. And I can have this terminal alkyne, right? And then it's being oxidized. Again, I'm oxidizing through this bond. I'm having 1, 2, 3 COOH, and then 1, 2, 3 COOO minus potassium plus carboxyl to carboxylate, right? But then I'm thinking about what can I do with this, right? Maybe this one is another elimination. So what can I do? I can have, again, alene, which also doesn't give me anything, right? Alene is here, right? But again, I cannot do anything with this one so that I can get carboxylic acid. Or I can have, again, diol as before, maybe with a substitution here. But again, assuming that iodine can do this kind of oxidation that I introduced in the previous slide, we actually get the same, the OOH, plus a mixture of this 1, 2, 3 carbon and the 1 carbon. Maybe we can assume that this is G, and because this is the same, as you can see, probably since we are doing it under basic condition, I actually have to write it like potassium plus O minus, and this is also O minus potassium plus. This is same as this one, so we don't choose this one, but we can choose this as our G, compound G and E are indeed homologs. So am I happy with this one? No. Why? Because first we are assuming that iodine is doing such diol oxidation, which is highly unlikely. We only see diol being oxidized like this with sodium periodate or PbO acetate 4. One of them is called malaprate oxidation. One of them is called Krieg oxidation. So I have never seen, honestly, iodine doing that. Maybe it's possible, but at least not in the introductory organic chemistry textbooks. Even in that case, F2G gives me a mixture of carboxylates, which is not good practical method, right? Because we don't want to get mixture of compounds. And if that was the case, maybe problem statement would have included that, oh, G is actually a mixture of product. Maybe G is the one that has smaller molecular weight. Something like this, kind of hint for us so that we can confirm this pathway. But this makes sense, maybe, but it's very edge case and it depends on many assumptions. So I am also eliminating this possibility. And now let's talk about this possibility where A is our terminal alkyne, right? Triple bond, then 1, 2, 3, and 4 carbon atoms. And then it gives me this geminal dibromide, right? And then I can do elimination. So I can move the triple bond to inside so that I can have internal alkyne. And then it's being oxidized to give 2 molecules of COOH. And then this COOH gives me carboxylate or minus potassium plus. So this one, there's nothing crazy. Now let's think about it. Potassium hydroxide, again, what we can have, again, go back to the original one, remove the hydrogens from here, if it's elimination. And if we are eliminating hydrogen from this carbon atom, we make a double bond here and the second pi bond. So we can go back to the original one. It does not make sense. Second one would be alene again, the double bond here. That also doesn't make sense. And the third option is like installing a triple bond here, which we already did. So maybe this elimination doesn't work here. So let's think about the substitution. And that's when the things get interesting. Maybe this OH minus acting as a nucleophile can maybe take the 1 bromine out. So we can have this structure like this. But bromine is good leaving group and we are having this under basic environment and the water. So maybe it can go here like this, and we can have bromine, and then we can actually get the ketone here. And this is very well-known reaction, what we call as haloform reaction, right? So now we're having this ketone, you can actually perform haloform reaction. Haloform reaction is one of those cases where you actually break carbon-carbon bond, and then that will give you this COO minus with a potassium as a counter ion, like carboxylate. And these are indeed homologous, right? They are both carboxylate ion, and then this one has 2 carbon atoms, and this one has 1, 2, 3 carbon atoms. So the key step here is that this is acting as a nucleophile, and it's converting geminal dibromide into a ketone. And the ketone reacts according to a haloform reaction. Specifically, we can call it iodoform reaction, and it gives us this. And then we also form HC iodine 3 as a precipitate. So as I mentioned, this reaction was used before when there was no spectroscopic techniques. They were using this method to find out the presence of methyl ketone, because methyl ketone is the only one that gives this kind of reaction, and then we have a precipitate. And specifically in the case of iodine, this one is a yellow precipitate. So whenever they have a ketone, but they don't know the location of the double bond, is it the methyl ketone, or maybe it's the far towards the inside, maybe it's ethyl ketone or more, they were doing this reaction, and whenever they see this yellow precipitate, they were realizing that this is methyl ketone, our original compound. So this reaction was used before to find out the presence of the methyl ketone. Basically, that's it. We found the structure of all compounds. So this is a terminal alkyne, this is a geminal dibromide, then internal alkyne, then acetic acid, and carboxylate, potassium carboxylate. And here, this is again geminal dibromide going to methyl ketone, and then we have this propionic acid, which is the homologous to E. So everything holds, and they want us to find out the structural formula, which we found, but they also want us to write the equations for every single reaction. And usually we are not used to write reaction equations in organic chemistry. That's something we heavily do in inorganic chemistry, like write the equation, also electrochemistry, right? We write the equation, then do balancing, and we don't usually write inorganic type reaction equations for organic synthesis, but they are asking us to write that. So honestly, it's not difficult, right? You just write this in the molecular form. You just write like C4H6 plus hydrogen bromide, 2 molecules, and this gives this. Are all easy, honestly. This part, like A to B, B to C, B to F, they're all easy. D to E are all actually the easiest one. It's just that simple acid-base reaction between acetic acid and potassium hydroxide, giving us a salt and water. I would like to talk about C to D, like writing the equation for them, and also F to G. Okay, these are the 2 things I would like to show. So potassium permanganate, right? How we are supposed to write the equation. So we know that potassium permanganate contains manganese in its highest oxidation state. So in type of oxidation reactions, actually it goes to Mn2+, right? It's our first half reaction. And the second one is we are used to write it as like organic form like this, right? And then this is like being formed 2 molecules of CH3COOA. But I would just set this aside. I would just write it as, just to help me to track the number of carbons, I would just write it as like this: C4H6 going to 12 C2H4O2. That's basically acetic acid, right? So let's try to balance. 1 mangan, that's balanced. 4 oxygen here, so we are adding 4 H2O here. So manganese O4. So manganese and oxygen are balanced. 4 hydrogens in acidic environment. It is actually acidic environment. We are adding 8 hydrogen plus. Even if it was basic environment, we would have done it with the hydrogen plus. We get the full equation, balanced equation, and then we would add OH minus to both sides. That's how we balance the equation in the basic conditions. But here it's an acidic condition, so it doesn't matter. So we add hydrogen plus. So 1 manganese, 4 oxygen, 8 hydrogen. Material balance is done. The last step is the charge balance. Here it's +8 -1, which is +7. And here it's +2. So we are adding our 5 electrons here. And I also want you to double confirm here that you will really understand what's going on, because actually the real thing that's happening in terms of like electrochemical is this manganese 7+ that's inside permanganate going to manganese 2+. Okay, so it needs to take 5 electrons so that it can go down to 2+. Okay, so what is really happening now? Let's add the same principles here. C4H6 got this. So number of carbon atoms, 4 carbon, 2 multiplied by 2, 4 carbon, it's done. Here we have 4 oxygens, so we are adding 4 molecules of water, right? So how many hydrogens we have here? 4 multiplied by 2, 8, plus 6. Here we have 14, and here we have 2 multiplied by 4, it's 8. So we need to add 6 hydrogen pluses. Okay, so hydrogen, oxygen, they are all matched. Now it's time to do charge balance. It's 6+ here, and it's 0 on the left-hand side. So we need to add 6 electrons. That's it, right? And now you see 5 electron here, 6 electron here. They have to be balanced. So you are multiplying this by 6 and you are multiplying this by 5. And then you add them up together. You end up with manganate minus plus 5 this internal, and then 18 hydrogen plus. It gives us 10 molecules of CH3COOH plus 6 manganese 2 plus 4 molecules of water. Okay, but they're really wanting you to write the full equation, so you need to add 6 potassium plus so that it's actually 6 potassium permanganate, right? And then for 18 hydrogen plus, honestly, they haven't specifically mentioned what kind of hydrogen plus they want. So honestly, this is true, keeping it like this. Oh, I also want to add 6 potassium plus on this side. But usually they use sulfuric acid. So instead of 18 hydrogen plus, I would have written it as 9H2SO4, okay? Just to keep everything neutral. You can probably also use that hydrochloric acid, but mostly they use sulfuric acid with potassium permanganate. And 4H2SO4 means that you need to add 4SO4 2 minus here. And sorry, 9SO4 2 minus. And 6 of them will be with this one, and the remaining would be potassium. So honestly, this one, it just becomes 6 mangan SO4 plus 3 sulfate. So you have your 5 molecules of alkyne, 6 molecules of potassium permanganate, and 9 molecules of H2SO4, giving you 10 molecules of COH acid, 4 molecules of water, 6 molecules of MnSO4, and 3 molecules of potassium SO4. So this is how you balance a reaction involving this permanganate oxidation. And also, yeah, it was a bit difficult to see it here at first because we are used to this kind of notation in organic chemistry, but you should also be able to write the reactions like this. Second thing is iodoform reaction balancing. That would need us to know the mechanism. So first we start with this one, and with potassium hydroxide, we form C, and then here we have minus, and here potassium plus water, right? And then what do? We take that negative that form here, and then it reacts with iodine 2, right? And then we form CO iodine plus potassium iodide, right? So, but you need to repeat it 3 times. So you know what I'm gonna do? I'm gonna not correct honestly, but just to save space and time, I'm just gonna write 3 OH here, and I'm gonna put 3 minus here, and 3 potassium plus, and 3 H2O. And 3 minus here, 3 potassium, is gonna react with a 3 iodine to form iodine and 3 potassium iodide. So it's basically repetition of these 2 steps 3 times, but I just condensed it under one. So honestly, it does not make sense at all. Like I want you to write anywhere, like a negative at once, because that's not how it happens, but it's actually 3 times repetition of these 2 steps that I wanted to write together. Now, once you have these, you continue with this one, CO, and then this is like 3 iodine, and then you have potassium OH, and OH minus attacks here. This goes up, this comes down, and this leaves. This is one of those rare cases that you actually have carbon with a negative charge. Usually carbon is not a good leaving group, but because it's connected to 3 iodine, and they are actually halogen that are negative charge by inductive effects, so that's why it's possible. And I also want to put potassium plus, and you end up with COOH plus potassium plus C iodine 3 minus. And obviously this is basic, so you need to have COH at the end. You need another molecule of potassium hydroxide, and then you end up with COO minus, potassium plus H2O. And also this one, potassium plus C iodine 3 minus, it also reacts with water to give us back the potassium hydroxide that we had, and H3 iodine 3, this yellow precipitate that we have. Now the best, most satisfactory part, that we are going to get rid of the things. I mean, a lot here and here, they go out, and this one goes out with this one. Potassium hydroxide here, H2Os are here, canceling out each other. And basically that's it. So you end up with having 1 molecule of initial methyl ketone, 3 plus 1, 4 potassium hydroxide, 3 molecules of iodine to give you 3 molecules of water, 3 molecules of potassium iodide. So we have all the equations, but I would like to talk about this more. This potassium hydroxide in alcohol favoring elimination, but potassium hydroxide in water favoring substitution. So you have like potassium hydroxide in water. It's just like, O minus, and it's a quite good nucleophile. So there's nothing that stops basically attacking like carbon, and then, kind of bromine in our case, and then doing this kind of substitution reaction, right? It's just a normal case. But what happens in ethanol? In ethanol, it's actually, there's a reaction between potassium hydroxide and ethanol. I'm just going to write it as ETOH. There's an equilibrium, and then you have ethoxide minus and potassium plus, okay? And let's see what's going to happen in this equilibrium. You have the pKa of ethanol is probably around 16, and the pKa of water, which is 15.7. Honestly, they are almost identical. Maybe the equation, because we know that in the acid-base equilibrium reactions, the equilibrium shifts to the side where there are weak acids and weak bases. So ethanol is actually slightly very weaker acid than water. So honestly, I would write this as slightly going to this side compared to this one. But the thing is that we are having alcoholic solution of potassium hydroxide. So which methanol is a solvent here, which means it's in large amount. It's a lot. So what does it mean? Because it's a lot, according to the Lattice principle, you will have a lot of them. So equilibrium will shift to the right because it's in excess, basically. So you will have maybe small amount of ethoxide in the reaction mixture, because having a weak acid as a ethoxide weak acid actually shifts the reaction to the left, but because it's in large excess, it's going to the right. So honestly, this equilibrium is like kind of between. It's not fully to the right or it's not fully to the left, but mostly because ethanol is a solvent, it will probably go a bit more to the right, I would say. But whatever the case, we have this small amount of ethoxide. So actually, in alcoholic solution of potassium hydroxide, like in the solution like this, it's actually ethoxide minus that's acting as a maybe nucleophile or a base, not OH minus. Okay, so as a base is stronger, okay, base than OH minus. Why? Because ethoxide, there's like alkyl is electron donating. So this negative charge in oxygen is actually less stable. So it wants to grab hydrogen and so that it can go to ethanol, right? So that's why it's a stronger base, okay, because of alkyl donation effect. And also you can just see it from the reaction equation, right? Because ethanol is a weaker acid, so its a conjugate base should be slightly stronger in compared to OH minus, right? So that's why this ethoxide is a stronger base. And also, in terms of nucleophilicity, like ethoxide versus OH minus. So this is a bulk here, right? Because of ethanol group. So this is actually better nucleophile, much more stronger nucleophile. This is a less nucleophilic, so it promotes elimination. And this OH is a better nucleophile, it promotes substitution. So basically the whole idea is that aqueous hydroxide actually contains OH minus and it just attacks as a nucleophile and favors the substitution. But alcoholic potassium hydroxide is actually ethoxide minus that's dominating. It's not OH minus. Okay? So when you see and compare these two cases, potassium hydroxide in ethanol and potassium hydroxide in water, you are actually comparing ethoxide ion and OH minus. And ethoxide promotes elimination and hydroxide promotes substitution. So that's the end of the problem. These are points that I wanted to talk about. And what we have learned, like using basic introductory level organic chemistry knowledge, but what we have learned extra is that maybe this special case maybe hasn't mentioned in the textbook, but we have talked about this alcoholic versus aqueous potassium hydroxide reactivity. We talked about how to convert like organic reactions, inorganic type reaction equations, integrating these two cases. Also, we learned about this case where we have geminal dibromide under substitution conditions with OH minus as a nucleophile. We can actually get a ketone. Yeah. And along the way, we also learned about the reactions, like when we explored those alternative pathways, we also learned these kind of reactions where we can actually have vicinal diols can be subject to oxidation, and we can actually cleave carbon-carbon bond.
And this is the end of the problem. One last thing before you go, if you found this video useful and you are serious about Chemistry Olympiad preparation, the workshop on August 23rd is designed exactly for you. Registration closes on August 18 or earlier if all spots are filled. The link is in the comments. See you there. Take care.